Hello everyone, and welcome to my presentation for Pitch Your Gen 4 Research Competition 2025. My name is Boualem Rais. I'm a research engineer at the French Atomic Energy Commission, called CEA. I define myself as a curious person, passionate about mechanics and materials science. And for me, working for nuclear energy is one of the most meaningful ways to contribute to the actual environmental challenges of humanity. Today, I will talk about a mechanical testing method I developed during my PhD to assess the fracture toughness of ODS steel's fuel claddings, which are candidates materials considered for sodium-cooled fast reactors, or SFRs. Fast reactors use fuel more efficiently and produce significantly less nuclear wastes than the current technology like PWRs. Among them, the sodium-cooled reactors, like the one showed in this schema, are the most mature technology of fast reactors in France. However, these improvements involve a more severe thermomechanical operating conditions. For example, fuel claddings operating temperature can reach 650 degrees C for SFRs, compared to around 300 degrees C for PWRs. Fuel claddings are located in the core of the reactor. If we zoom in, we can see that in this core there is an assembly of thin-walled tubes arranged in hexagon. This is these tubes that we call fuel claddings. Fuel cladding is a 4-meter long tube of around 10 mm diameter and 0.5 mm of thickness, in which we put the fuel pellets that produce the heat energy before transforming it to an electrical energy in another part of the reactor. This component is the first confining barrier of the radioactive fuel, and its integrity is important. One promising class of materials for the fuel cladding of SFRs are the martensitic and ferritic ODS steels containing 9% or 14% of chromium. These materials are known for their high temperature mechanical strength, but their low ductility raises concerns about their fracture toughness. So assessing this property is then essential, but the fracture mechanics standard testing methods lack the specimen geometry and the geometric parameters for these so thin-walled tubes. To address this, a new specimen and test methodology named Miniaturized Ring Notched Bend test was developed using a combination of finite element modeling and experimental testing. This method allowed us to directly measure the fracture toughness and the crack growth resistance on a single specimen directly machined from the fuel cladding. The results obtained for both 9 chromium and 14 chromium ODS steels showed that their fracture toughness exceeds the safety criteria, confirming their suitability for SFRs. To conclude, this new test method contributes to the deployment of Generation 4 reactors by helping to ensure the reliability of advanced fuel cladding materials for actual and future nuclear systems, and by making Generation 4 reactors safer. Thank you.